Hey everyone, we're going to solve this problem. You have to find the limit of this series. Now at the first glance it may look very simple and straightforward, but it's actually not. Why is it actually not? I'm going to explore. We're going to explore together. And I will also explain to you why it looks simple, but there's a subtle difference in what you're thinking and what this problem says. So if you observe it carefully, that you can see that this e to the power minus n and n to the power k by k factorial immediately trigger the Taylor series of e to the power n. So what is the Taylor series of e to the power n? And you can think, okay, if you take the e to the power n outside and you take the summation, it's e to the power n and that gets cancelled, right? So you are thinking of something like this. You're thinking of limit n tends to infinity summation of, so you take the e to the power n outside and you have a summation here which goes from k from 0 to n to the power k by k factorial. And you can think that, okay, limit n tends to the infinity, this goes to e to the power n and e to the power n and e to the power minus n gets cancelled out. But that's not going to happen here. The reason being, e to the power minus e to the power n's definition is not dependent on n. So what is e to the power n? Let's write that. So e to the power n is summation, let's take a different variable, I from 0 to m n to the power I by I factorial. But you can also use k here, not a problem. K from 0 to m, k factorial n to the power k. So observe here, and then limit m tends to infinity. So you see n is a constant here. Here's a limit on n, but here n is a constant. So you see we need to use a different variable. It's not n here, it's m here. So the main issue that why we cannot use the e to the power limit is that this term is dependent on n, not a different variable, so that you can take the limit inside and take the e to the power n outside. So e to the power minus n and this both are dependent on n, so you cannot take the e to the power n minus outside and take the limit inside. Does it make sense, all of you? Very good. So the e to the power n, again I'm repeating, e to the power minus n cannot be taken outside, and you cannot take the limit n tends to infinity inside, so that it turns out to be e to the power n. So this is the basic idea. So how do we solve this? If you're aware of probability, this is the beauty of real understand probability. There's a lot of connection, there's a lot of depth, there's a lot of beauty and kind of dynamics between both of them. So if you think that this is kind of the Poisson distribution, so I will erase it. So this is kind of the Poisson distribution. So let's revise Poisson distribution. So if x is a random variable, x follows Poisson lambda with parameter lambda, then the PMF of x, because it's a discrete distribution, so let's call it P of k. PMF of x taking the value k is nothing but this quantity, where not this quantity but e to the power minus lambda to the power k by k factorial, right? So if you put lambda is equal to n, you get P of nk is equal to e to the power minus n to the power k by k factorial. So what does it turn out to be? So this turns out to be limit n tends to infinity summation of k from 0 to n Pn k. Or you can also write as P of xn is equal to k. What is xn? So xn is nothing but, so you can write that. Now you can write as xn is nothing but follows Poisson n, right? This is how you can write it. So let's rewrite this. So if you rewrite this, so what is this quantity? This quantity is nothing but the CDF till point n. So probability xn less than equal to n. Beautiful, right? Now it is asked to find the limit n tends to infinity xn less than equal to n. Do you remember? This is where you to bring your memories of probability theory. Do you remember where there is a limit on the CDF? It's used in convergence in distribution. Convergence in distribution of random variables. This is asking you where this xn less than equal to n, this quantity is converging to in distribution, kind of. So, and the most famous result in convergence in distribution is nothing but the central limit theorem. So, the thing is that we will now find out for central limit theorem we need a mean, right? So, we will find out that can you express this as a mean, as this distribution, can you find some mean out there? And the beautiful result is a Poincare distribution is additive. So xn can be thought of summation of Poincare, n Poincare independent Poincare ones, n independent Poincare ones. So you can rewrite it as summation of pi, where each of the pi's are IID Poincare 1 because of the additive property of Poincare distribution. So therefore, you can write it like this, and you can write it as limit n tends to infinity probability summation of pi okay. So now if you remember central limit theorem, so let's revise what central limit theorem does. To do that, let me erase this. So if you remember central limit theorem, you will see that if Sn is the sum of some random variables, let's say ai, I from 1 to n, right? Then central limit theorem says that in Sn minus the mu of this, the mean of this, okay, mu n by sigma n, okay, sigma n of this converges in distribution to normal 0, 1. So you cannot realize this two right now, so you have to right now use the essentially what the in distribution convergence means. We have to write down the CDF form of that and in distribution convergence. So the CDF form of distribution convergence means probability Sn minus mu n by sigma n less than equal to x. This converge, so this probability as n tends to infinity, this probability converges to z less than equal to x, where z is a normal distribution. So this is the definition of central limit theorem. So how do we use that here? So here Sn is nothing but xn, if you remember. Here xn is nothing but summation of I from 1 to n pi, okay, and so here Sn is equal to xn, so here xn minus mu n, so what is the sum mu n, the Poincare mu is n, what is the sigma n of that, the standard deviation root n, So now remember that we have to rewrite this in this form. So it goes to that side, n goes to that side, so this becomes less than or equal to 0. And this n tends to infinity, we know it converges to, so here it's x is equal to 0. So it converges to, this is equal to probability z, not standard normal, less than or equal to 0, because x is equal to 0 here. And you know, since standard normal, here it's symmetric around 0, so there is, oops, so there is the area is half. So this is half. Does it make sense, all of you? This is a beautiful problem where you see that a series problem, which since it's not natural to you, can only be solved using probability theory. This is the beauty of central limit theorem. And the reason being, if you try to write even the sequence form out of the series, you will see that this internal summation changes because n goes to n plus 1. So the entire distribution changes. And it's very hard to solve it using the usual series ideas. So next time whenever you're solving a series problem, think, when it's becoming difficult, can you solve it using central limit theorem? I hope you found this beautiful as I found it. I will see you in the next video. Bye-bye.